Transmission lines. Introduction. Series on transmission line theory. Lecture number 1.10. Transmission lines are multi-conductor, passive, linear systems widely used and useful to transfer a telecom signal or electrical energy or both from one point to another point. In the present session, the focus is on providing an introduction to transmission lines covering various aspects pertaining to transmission lines. Here we cover definition of transmission line, several examples, applications, losses, functioning or operation, and also types of lines widely used. Transmission lines are linear, passive, multi-conductor systems. These are used primarily either to transfer low frequency electrical energy or high frequency telecom signal or both in TEM form from one point to another. This is a definition for transmission lines. The conductors in the line are separated by insulators or by air. Usually source and destination points are separated by considerable distances. These are multi-conductor systems. So conductors are separated by insulators or air. Lines are used to transfer signal or energy from one point to another point. These 2 points are usually separated by considerable distances. Here is shown a H that illustrates the functioning of transmission line. In this line, there are 2 conductors. They are running parallel to each other. That's why this line is called parallel wire line. On one side, signal source is connected. It may be energy source also. On the other end, load is connected. Left side where source is connected, it is called source end. Right side where load is connected, it is called load end. Different names are there for source end. It is also called input end. It's also called sending end. Similarly, for load end, names are there: output end, receiving end. Here is shown a symbol of the line. 2 conductors separated by some distance. A variety of lines are available. They are shown here. In A, coaxial line, it consists of an inner conductor, outer conductor separated by a dielectric. Diameter of inner conductor is usually indicated by 2A. Inner diameter of the outer conductor is indicated by 2B here. Coaxial line. 2-wire line. 2 conductors, parallel conductors, they are running side by side, separated by distance D. Diameter of each conductor is 2A. These are widely used, commonly seen lines. 2-wire line is a low frequency line, whereas coaxial line, usually it is used at high frequencies. Parallel plate line is also there. 2 plates separated by certain distance. Metal plates are separated by distance. Similarly, strip line, micro strip line. In strip line, 2 metal plates are there. In between, there is dielectric. Within the dielectric, there is a strip running. You can see here. In micro strip line, the metal plate is there. Over that, there is a dielectric. Above dielectric, a small strip is running. C, D, and E, parallel plate line, strip line, micro strip line. These are widely used in microwave integrated circuit technology. The micro strip transmission line, a geometry is shown. Already it is indicated in the previous slide. Here the specialty is the structure is illustrated completely. This is while it is functioning. This is conductor. Okay. This one is a small strip, conductor strip. This is dielectric. When it is working, here is shown electric and magnetic field lines or flux lines. Continuous lines denote electric field, whereas discontinuous lines, they are indicating magnetic field lines. So signal is fed at one end, received by on the other end. The travel is along the length of the strip. As already mentioned, these structures are used in microwave integrated circuit technology. Prominent examples for transmission lines are multi-conductor parallel wire system carrying low frequency power to run heaters, fans, motors, etc. By the side of the road, you can find wires, conductors running over the poles. Sometimes 3 wires, sometimes 6 wires, 10 wires, several wires, but running several number of wires running parallel to each other over the poles. They are examples. They carry energy. They are capable of carrying low frequencies. At high frequencies, they suffer with one disadvantage, a serious disadvantage. At high frequencies, they tend to radiate. It means the energy simply escapes into space, never returning back. It amounts to loss. So, parallel wire systems are low frequency transmission lines. Coaxial lines. These are also lines. They carry high frequency. They are capable of carrying high frequency, like video signals to domestic TV sets. Certain media do what TLs do, but they are not TLs. For example, hollow pipe waveguides. Their purpose is same as the purpose of transmission lines, but they are not called transmission lines. Why? What is the reason? If we consider hollow pipe waveguides, we call them simply waveguides. We don't call them transmission lines. The reason is they are single conductor systems. Transmission lines are by definition multi-conductor systems. Hence, they cannot be called hollow pipe waveguides, cannot be called transmission lines because they are not fit into the definition of transmission. Another reason is also there. In hollow pipe waveguides, signal travel is in the form of a non-TEM wave, whereas transmission lines, by definition, they carry signal in TEM form. So, 2-3 differences are there. Because of those differences, pipe waveguides, they don't fit into definition of transmission lines. Optical fiber. Optical fiber is a dielectric. By definition, transmission line is a conductor system, but optic fiber is dielectric. So, this also is not fit to the definition of transmission line. Free space is not transmission line. Even though the wave is TEM, it is not conductor. Free space is not a conductor. In fact, it is an insulator medium, and hence it cannot be called transmission line. Several applications are there for transmission lines. They can be broadly categorized into primary and secondary. Primary application is to transfer signal and or electric power. This is the primary application of transmission line. Secondary applications, they are useful to simulate circuit elements. What are circuit elements? Resistance, capacitance, inductance, etc., etc. Are they useful to design circuit elements, particularly inductor and capacitor that can work at high frequencies. These are also used as resonant circuit. They act as resonant circuit, series resonant circuit, parallel resonant circuit and all. Another secondary application is they can act as a step-up transformer. If you give small voltage at its output terminals, you can find more voltage, large voltage. They are also useful in impedance measurement. They are also useful for load matching purpose. Note, secondary applications, most of them, they pertain to high frequency applications. At higher frequencies, a brief regarding secondary applications. At higher frequencies, particularly in gigahertz range, it is quite hard to realize lumped elements. Short or open circuited line pieces are usually used conveniently for that purpose. A resistor, inductor, capacitor, which you can find in the laboratory, they work only up to certain frequency. Beyond that frequency, if you go beyond that frequency, they don't work. So, if you want capacitor, what to do? If you want inductor, what to do? What is normally done is a piece of transmission line. It is taken and wherever it, whatever is required is done by a short or open on one end. Now it acts as capacitor or inductor depending upon its length. We can see, we are going to see a short circuited lossless line. Here is a lossless line. What is lossless line? We are going to see. A lossless line, you consider a lossless line. It is short circuited. At one end, this fellow, it acts as an inductor. When length L is less than lambda by 4. When length is in between lambda by 4 and lambda by 2, it acts as a capacitor. When length is n lambda by 4, n is odd integer, then it acts as a parallel resonant circuit. When n is an even integer, it acts as a series resonant circuit. An open circuited lossless line. You take a lossless line, length L, it is open circuited. Here on the other end, here it is a capacitor. When length is less than lambda by 4, when length is between lambda by 4 and lambda by 2, it acts as an inductor. When length is n lambda by 4, n is odd integer, then it acts as series resonant circuit. When n is even integer, it acts as parallel resonant circuit. Line pieces can also be used for use as a step-up transformer. Suppose I have some voltage here, let us say 2 volts. I want to have 10 volts. How to step up? If it is low frequency, you can use a transformer. But all your transformers, they don't work in the gigahertz range. So some new technique, some new design is to be resorted to. So line pieces are used for that purpose. They are useful. An open circuited lambda by 4 line is capable of stepping up the voltage by a huge amount. Let us say there's a line, open circuited line, length is lambda by 4. If you give small voltage here, actually infinite, very huge voltage is supposed to appear here. Not infinite, very huge. Infinity, zero, etc. These are not achievable in practice. Other resonant circuits are also capable of giving more voltage currents than is given at its input terminal. So pieces of lines are useful to step up the voltage. Impedance measurement. Another secondary application is measurement of phase is difficult at high frequencies. Hence, at megahertz or gigahertz range, direct measurement of impedance, ratio of voltage to current, naturally is not at all easy, and sometimes it is even impossible. To overcome this complication, measurement setup is designed using a piece of transmission line called slotted section. With this arrangement, by making measurements on standing wave pattern within the slotted section, one can find impedance of load at higher frequencies. What is impedance? It is complex voltage by complex current. Complex means magnitude and also angle. So first you have to find out magnitude of voltage, magnitude of current, phase of voltage, phase of current, and then you have to consider the ratio. But finding angle is quite difficult. Setting up the reference and all that, complicated matter. So it is ordinarily it is not possible, particularly at high frequencies. It is quite difficult finding voltage. Another serious problem is in megahertz range, gigahertz range, voltages and currents, they are not used. The concept of voltage, the concept of current or voltage current quantities, they give way to fields, electric field, magnetic field. So impedance, which is defined in terms of V and I, that also becomes, that definition becomes somewhat irrelevant. Anyway, impedance measurement at gigahertz range or at the higher end of megahertz range, it is done with the help of slotted section. What is slotted section? It is a transmission line. So we are describing various secondary applications of lines. Load matching, another secondary application of transmission line is load matching. What is load matching? Suppose there is a transmission line and you have given a signal here at the input terminal. So you expect this signal to be delivered to the load at the load end. Here, you want everything of the signal to enter into the load. But it can happen only when characteristic impedance is equal to load impedance, characteristic impedance of the line. Or for the timing, let us say, when certain conditions are met. When there exists certain kind of matching between load and line, then signal is entirely delivered to the load. Otherwise, what happens is, the delivery is partial, remaining signal returns back, travels towards the source. This is called reflected wave. Reflected wave is harmful to the functioning of the line. It increases losses, reducing the efficiency, it reduces the capacity. So many other serious problems exist. So certain techniques got developed by which reflected wave is eliminated from the line. That techniques are called load matching technique. These load matching techniques use pieces of transmission lines. They are called quarter wave transformers or stubs. To avoid reflections over the line, load matching is undertaken either by using quarter wave transformers or stubs. A quarter wave transformer is a line of length lambda by 4. Quarter means lambda by 4. And stubs are line pieces with short circuit load. Lines can be claimed load matching as one of their important applications. So stubs, quarter wave transformers, these are pieces of lines. They are used for load matching purpose. Load matching is one, that's why it is considered as one of the secondary applications. Line is supposed to carry the signal from one point to another point. While carrying, the line itself consumes, it takes power from the signal and consumes it, leading to losses. The signal, because of the losses, the signal while traveling over the line undergoes certain amount of attenuation. What are the causes of the losses? we will see here. The lines are used to transmit signal in the form of voltage or current. However, while traveling, the signal gets dissipated, incurring certain losses. These losses can be divided into three types: radiation losses, losses due to conductor resistance, losses due to dielectric conductance. So for understanding, we consider a small line. The signal is traveling. This is electrical signal. Now, this is open wire line. It is open, it is in the space. So what happens is radiation occurs. Signal tends to escape into space. The nature of the signal is, it is found, the nature of the signal is such that with increasing frequency, it has more tendency to escape. So signals of high frequencies, they tend to escape into space to return back never again. It amounts to losses. These losses are called radiation loss because it is radiation escaping into space from the wire is radiation. Resultant losses are called radiation losses. Now, losses due to conductor resistance. These are conductors. Line is consisting of conductors. Usually the lines are made with good conductors, but not perfect conductors. Good conductors, however small it may be, they have certain amount of resistance. So these conductors have certain resistance. Usually it is small. Now signal journey is in the form of currents through the conductor. So certain amount of current flows. These currents gives rise to certain amount of losses. Those losses according to Joule's law equal to I square R. This much amount of power gets converted, signal power gets converted into heat according to Joule's law. So signal power is getting converted into heat. So therefore signal is losing its strength, leading to attenuation. The losses are there because of non-zero R. Then losses due to dielectric conductance. See, these two conductors, they are separated by certain dielectric. This dielectric is not an ideal one. Conductivity of this dielectric is, it is not zero. It is not zero. Therefore, what happens is certain currents flow from one conductor to another conductor through the dielectric. These currents are called leakage currents, and these leakage currents are modeled by assuming certain amount of conductance to the dielectric. It is supposed to be zero, but it is not zero by assuming small amount of conductivity to this fellow. Now, while currents are flowing through the dielectric, here also certain heat get generated. Joule's law, according to Joule's law, that heat is, of course, is V square by R. R is resistance of, V is voltage difference between the conductors or voltage across the dielectric, and R is resistance of the dielectric. Usually these three types of losses are present, and when we consider coaxial line, radiation losses are opposite. They are absent while remaining two are present. If you consider parallel wire line, all the three are present. A few points regarding radiation losses. Radiation losses exist in lines which are open to space, and it is due to escape of some of the power flowing over the line into space. Obviously, they are absent in enclosed lines like coaxial lines. This type of losses arise because the line acts as an antenna in open spaces, shedding out the energy which it is supposed to carry. Radiation losses. These losses can happen only when line is carrying AC, with the separation between the conductors equal to an appreciable fraction of one wavelength. Radiation theory is necessary to calculate these losses. Ohmic losses. The conductors of the line while carrying currents dissipate signal power as ohmic losses due to their resistance, resulting in conductor heating. Conductor heating or I square R losses are proportional to current through the conductors and hence inversely proportional to characteristic impedance of the line, about which we are going to discuss very soon. They are also frequency dependent, increasing with frequency due to skin effect. What is skin effect? It is found, let us consider a conductor, thick conductor, and some current is running through this conductor. It is found, if the current is AC, it is found the current through the cross section, it is not uniform. The current they found, it is concentrated at the edges, somewhere here, over the edges. The concentration is more and more near the moving towards periphery as frequency is increased. Okay, when frequency is decreased, the spread of this current over the cross section becomes more and more uniform. But with increase in frequency, concentration is more and more at the periphery. So R is rho resistivity length by A. A is cross-sectional area. Effective cross-sectional area now is dependent upon frequency. If it is DC, entire total current is spread uniformly over the cross-section. When frequency is high, the current is concentrated near to the periphery. Now area is small. When area is small at high frequency, naturally resistance also increases. This is called skin effect. Area variation, effective cross-sectional area variation with frequency of the current. It is called skin effect. Dielectric classes. The dielectric that exists between the conductors of the line is not usually perfect one, and hence it possesses certain amount of conductance G, moles per meter. As a result, it allows the currents to flow from one conductor to another, resulting in dielectric heating. There it is conductor heating, here it is dielectric heating. Usually these losses increase with frequency, and as the current is proportional to voltage across the dielectric losses and consequent heating are also proportional to the voltage across the dielectric and inversely proportional to characteristic impedance of the line. Conductor losses, dielectric losses together. The combined conductor and dielectric losses of a line can be computed in terms of resistance and conductance. Resistance and conductance, these are part of primary constants about which we are going to discuss. So, the time average power dissipated is simply sum of the two contributions from the series resistance and parallel conductance. See, this is resistance, this is conductance, this is voltage, this is current, off, because these are phases. Classification is there. One classification is into parallel wire lines and coaxial lines. A few points regarding this classification. This type of lines, parallel wire conductor transmission lines. These lines consist of a pair of conductors running parallel to each other. Usually insulator spacers are used to maintain fixed distance between the wires. These are widely used in power systems, telephone lines. Well-known examples are open wire lines, twin lead ribbon cables, twisted pair cables, etc. Sometimes conductors are maintained parallel to each other with the help of plastics like phenolic or polystyrene. In such case, line is called twin lead cable, which can be considered as a hybrid between air insulated parallel wire lines and coaxial cables. They have the advantage of being lighter, less bulky, very easy to install. What he is trying to tell is, normally over the poles by the side of the road, you can find wires running parallel to each other. Whenever there is a danger of these conductors touching each other, then what they do is they use certain plastic spacers. So these spacers maintain distance between them fixed. To make spacers, plastics like phenolic, polystyrene, etc. are used. Twisted pair, invented by Graham Bell, in which two conductors are twisted together, falls in this category. Twisting helps in cancelling out interference or crosstalk from external sources. These are well suited for low frequency applications. High frequencies, they are useless as their dielectric losses increase and they also tend to radiate. As these lines are usually without any shield, they are highly susceptible to noise pickup. When line is running in open space, there is every possibility for the conductors to pick up the voltages that are there surrounding the conductors. I mean the signal that is surrounding the conductors. So many signals are there, so many radiations are there on this earth, and these radiations, they are there in the atmosphere running around the earth. So there is every possibility to pick up these noise components from the surroundings by the conductors. Now coaxial lines, few points. These lines consist of an inner solid conductor and an outer coaxial conducting sheet. Inner conductor, outer conductor, separated by dielectric medium. This is the structure. In these lines, radiation and dielectric losses are very small. Due to the presence of shield, external interference also becomes negligibly small. That's why coaxial line has become so popular popular among telecom lines. These lines are extensively used in high-frequency applications like TV cables, telephone cables, power cables, etc. Solid, flexible type cables give smaller losses, but rigid air-filled cables are relatively expensive. Coaxials are suited for unbalanced mode of operation. Balanced and unbalanced we will see later. Here a comparison is given between circuit theory plus wave theory, their role in transmission line theory. You see, in circuit theory, voltages are used, currents are used, and it is useful at low frequencies. In wave theory, wave nature is taken into consideration, or it is about wave nature. Wave theory is about wave nature, delay, etc. This wave nature is pronounced at high frequencies. So circuit theory is at low frequencies, wave theory is applicable at high frequencies. Wave theory is applicable at low frequencies also, but at low frequencies we use circuit theory. Reason is circuit theory is simple, easy, right? Now transmission line theory. Transmission line theory is valid at all frequencies, 0 to infinity. We consider all frequencies, and it is analyzed in terms of voltages. It is we use currents also in transmission line theory. We use wave nature also. It is taken into account, delay, wave nature, all those things that we studied in field theory. All those things are also taken into consideration. So basic point here is transmission line theory uses voltages and currents pertaining to circuit theory. Not only that, it uses or it employs the delay and wave nature, which was investigated while studying wave theory. Both these aspects combined you can find in transmission line theory. So these are some of the things which I want to share with you regarding introduction to transmission lines.